I will chair the session together with Professor Kumar. And our first presentation will be given by Professor Herbert Schneckenburger from Germany. And the title of the presentation is Leaf Cell Microscopy Moving Towards Nanometer Dimensions. Please, Herbert, go ahead, share your slides, and let's start the presentation.
Okay, thank you very much for your kind invitation. Unfortunately, I only received it yesterday in the afternoon, and so I had to prepare my lecture a little bit in a hurry. Nevertheless, I hope it will be okay and I can tell you some interesting things. I will try to share my screen. The browser verhindert. Oh, that's a little problem for sharing.
Так як мені приєднати мої слайди? От у мене от слайди.
Please let Professor Schneckenburger to proceed with the presentation, because now we see as you. So Alexander Demchenko, we see you now. Can you switch off the microphone and the video?
We turn off your microphone.
Okay.
Right. Let's try to open the slides.
Green button.
Now it seems that it would be possible.
Okay.
Now we see something, but it's.
You see something. Yeah, you see a little bit more, and I will try to improve it still. We go to the presentation mode.
Yep.
Now I lost it. I will try again in the presentation mode.
You're right.
Now it should be okay.
I don't.
Okay,
I think you have to. Sorry, I think you have to unshare and share the PowerPoint. So you have to share an application.
You don't see my presentation?
No, we see a window with the list of files.
Right.
Okay, I will try it again. I will close it and try to reopen. You see here a list of files?
Yes.
Yeah, we see a list of files.
Yeah, but I think you're sharing that window rather than the window of PowerPoint.
You don't see my PowerPoint now?
No.
Yeah, you have to share the window of PowerPoint.
So I think you have to. You have to
open
stop sharing.
I will try it again. I will.
So you have to first open the presentation in PowerPoint and then share it.
Yeah. Okay, PowerPoint.
So first you open in your PowerPoint presentation and only then share it.
Notify.
Yes.
Erlauben. Is it okay now?
No. Now we don't see any file that you share.
Okay.
If you press that green arrow to share and then select the PowerPoint presentation.
Is it okay now?
Now we see, yes.
Okay. Sorry for all inconveniences.
It's
I
okay.
will try to go the presentation mode. Is this also okay?
Now you can press
Run
the,
your presentation, please.
yes. Now you can press how do you call it?
Do you see my presentation now?
Yeah, we see your presentation, but you can go to the presentation mode. Now we have all the how to. Well, it's a little sign like a screen at the bottom, close to to Zoom. If you
Okay.
press it,
Press F5, please.
I
Press
will go
5.
back to this. Do you see something in this mode?
Yeah, we see your slides, but you can make it full screen.
Yes, I did it.
Ah, you did it.
I'm now in full screen.
Or change your slides by hand from one to another. Change handily from one to another to scroll the presentation.
Okay.
Press
So
F5.
yeah,
F5.
F5. No, I'm here. So I will do the following. I will remain in this mode, and I think you see in the presentation.
Yeah, we see the slides.
I will remain here because the presentation mode doesn't seem to work for you. I don't know any reason.
Yes, I see.
So I will remain here.
All right, let's go ahead. We see everything what is on slides.
Okay, so I will go ahead. Maybe I can make it a little bit larger. The subject is moving towards nanometer dimensions, and I would add in life sciences because that makes a little bit difference. And everybody here will be acquainted with microscopy. We need a microscope for going to micrometer or nanometer dimensions. I have here the scheme of a microscope, and what is most essential is the numerical aperture of the objective lens. And usually, when using the Abbe criterion, we can come down to about 200 nanometers. So that's a matter of fact since the time of Ernst Abbe in the 19th century. This is for transmission microscopy. In life sciences, mostly fluorescence microscopy is used for measuring metabolites, dyes in cells, for measuring cytotoxic drugs, for measuring cell substrate contacts. And in this case, shortwave light is irradiated to the samples and longer wave light is detected. Usually we use here the LERAY criterion, which determines the diffraction of a single beam. And again, we are around 200 nanometers. And the question is, can we go below this value? The first thing is people try to do 3D microscopy using either a laser scanning microscope where the focused laser beam is scanned over a cell or a sample, and longer wave fluorescence is selected by a pinhole so that you can only get signals from individual planes, and you can scan the planes up and down. The next point would be light sheet microscopy. Use a light sheet coming from the side, move it up and down, and measure, for example, these cell spheroids. And finally, you can also do that with total internal reflection microscopy, changing the angle, the incidence angle on your samples, and thus changing the penetration depth of an evanescent field from maybe 50 or 70 to some 100 nanometers. So these are possibilities of 3D microscopy. But now I would like to come to super resolution microscopy beyond the Abbe criterion. And the question is, what can be done here? One possibility is structured illumination microscopy. In this case, we use the interference of 2 or maybe more laser dyes, and we have some spatial frequency, and the spatial frequencies of our interference and of our objective lens sum up to get a higher resolution. In our case, we can double the resolution from about 200 nanometers to 100 nanometers. And if we use speeds of 200 nanometer size, we can now much better resolve these speeds. There are other possibilities. There is, for example, LERAY scan microscopy, where we do the following. Instead of confocal, of using a small pinhole, we use multiple detectors. So instead, for this LERAY function, instead of measuring the whole function, the whole beam, we measure individual spots with different detectors, and this helps us to improve our resolution now. There's a little problem. Do we still see it?
Yes.
Yes, we see.
I have a problem to forward my screens now. What happens? I have a problem with my screen now. Sorry. I cannot move it. I try.
Is it frozen or what?
It's frozen, yes. It's frozen.
Maybe it's connected to the internet connection problem.
I don't know. I will try to stop and try to do it again.
Mm-hmm.
I will try to do it again.
All right.
Now I'm here. Do you see it?
Yes, we see it.
Okay, so I come back here. I want to mention different other methods like single molecule localization microscopy, where each molecule is registered n times, and if I measure single molecules, the resolution is enhanced by the square root of these n times, and so I can come down to about 20 nanometers. And finally, some of you may know the stimulated emission depletion microscopy described by Stefan Hell first in the 1990s, where you have an excitation beam and a high-power depletion beam, where in the outer parts of your light beam you have stimulated emission, and so the fluorescence is confined to a central spot, so we can come down to about 50 nanometers. So these are possibilities to enhance the resolution. For structured illumination, I'm just showing you the optical transfer functions, which are enhanced by this structured illumination, so we can double our resolution. And in the case of living cells, we have here a cell with a cell nucleus and some microtubules. And when going from conventional to super resolution microscopy, we can increase the half width from about 190 to 15 nanometers. This is an example for single molecule detection, where from this kind of image, we can come to this kind of image, imaging single molecules. And in the case of state microscopy, we have the excitation of our sample here. We have the depletion here. And what remains for fluorescence excitation is the central part. Problem is that for single molecule detection and for this TET microscopy, you use very high powers of light, and this may create problems for live cell microscopy. Just to mention, there is a method which is called MinFlux, also developed by the Health Group. If you measure or if you track your molecule at the position of minimum light exposure, you may come down to a resolution of about 2 nanometers, and you have only moderate light exposure. Perhaps this will be a technique for the future. Just to show you how you can increase a resolution in Z, in vertical direction, this can be done by total internal reflection microscopy. And when you change the angle of incidence, you may find an algorithm that helps you to fit distances in the range of 10 nanometers or even less. You can also combine structured illumination for super resolution and turf microscopy to get super resolution both in lateral and in axial direction. This is shown here with two interfering beams, both hitting the sample under total internal reflection conditions. And an example is given for the case that glucose transporters are moved from intracellular vesicles to the plasma membrane. Here only with structured illumination microscopy, you see the vesicles. And here for structured illumination and total internal reflection, where you see a white fluorescence of the whole cell membrane. I should mention something else. This is isotropic resolution. Usually you have high resolution in lateral direction here, but less high resolution in vertical resolution, giving you this kind of point spread function. And one possibility would be to rotate your sample, and then you would have an isotropic high resolution. Unfortunately, the presentation mode doesn't work. Otherwise, you could see the rotation of these samples. In this case, we have our samples not on object slides, but in small capillaries, which we can rotate by different angles. Finally, I would like to mention one thing, perhaps you may know it. It's FRET, or phosphoresonance energy transfer microscopy. Let me come here. If you have two molecules in close vicinity, it may be possible that you excite one molecule and transfer your energy radiationless to a second molecule, a so-called acceptor. And this helps you to measure the proximity of two kinds of molecules. For example, this base, beta secretase, and APP, amyloid precursor protein, which play a role in the pathogenesis of Alzheimer's disease. So this is not real imaging, but it's a measurement of distances below 10 nanometers. I think I would like to give you an example, but I have an impression my time is already over due to technical problems. Therefore, I come to the two final slides. I have, as a summary, I can say we have conventional resolution in transillumination of fluorescence microscopy around 200 nanometers. We can improve this resolution to about 140 nanometers using area scan microscopy. We can use structured illumination and can come to 100 nanometers. By STED microscopy, stimulated emission depletion microscopy, we can come down to 30 to 70 nanometers. By single molecule localization to 10 to 20 nanometers. And by MinFlux microscopy to values down to 2 nanometers. Infrared microscopy allows you to probe distances below 10 nanometers. I talked about special configurations like variable angle, total internal reflection microscopy, axial tomography. And finally, my last message would be if you work with living systems, you have to care about the amount of light to avoid phototoxicity, assuming tolerable light doses, which often are around 10 joules per square centimeter, and an irradiance of 100 milliwatts per square centimeter that corresponds to solar irradiation. You could measure in a recording time of 1 second about 100 images by wide field microscopy, about 10 images by structured illumination microscopy, because for each image you need at least 9 raw images. For confocal microscopy, you may be able to record 20 images. That would be from a cell from up to down of your cell or of your sample. In light sheet microscopy, it's better than for confocal laser scanning microscopy because you illuminate not the whole sample, but only the slides which you are going to measure. And for single microscopy and state microscopy, you should take less than 1 image. That means you could record more or less 1 snapshot. So that's the end of my message. Sorry for some technical problems. I would like to thank everybody here for its attention. I cannot say it in Ukrainian, in Russian, Spasiba za vaše vнимание. In Ukrainian, it may be something similar. So thanks to everybody.
Thank you very much for your educative and fascinating presentation. And I think that we can steal some time from Alexander's presentation and ask some questions. Please, if anybody has a question, you can just switch on your microphone and ask the question.
May I ask a question?
Please.
For your opinion, what is the best technique for super resolution for a live cell from a point of view of their non-destructive diagnostics?
To my opinion, a method which works quite reliably is structured illumination microscopy, because once you have set up your experiment, you can use it and have a benefit of a factor 2 in resolution. So this is what works reliably. For these high resolution techniques like single molecule or STET microscopy, you have a great risk that you might damage your sample, and you could rather take a snapshot than maybe a series of experiments. And I think the MinFlux technique is still in the stage of development. Maybe it will resolve the techniques, the problems in the future. But for the moment, I would say structured illumination is the most reliable technique.
Okay, thank you very much.
All right, and please, Igor, go ahead with your question.
Thank you very much for your excellent presentation. And can you say something, in your opinion, can we enhance the resolution in future for optical microscope?
Okay, so for me, the limit of enhancement, the limit is indeed this MinFlux or some related technique. So we can go down to the nanometer range. Also for this single molecule technique, we can go down to the nanometer range. We should consider that our detectors become more and more sensitive, and so we need less and less light for our experiments. So I would say we can come down to the range of 10 nanometers, but it's really a question of well setting up your experiment and of well reducing your light power. But I think in the order of 10 nanometers, we might arrive at one time.
Thank you.
All right, I think that we have to move ahead. Thank you again for your presentation. And our next speaker is Alexander Demchenko with their presentation on molecular machines. Alexander, you can start sharing your. Herbert, you can stop sharing your slides so that Alexander can.
Yes, how to do that? Oh,
there is a green button.
yes.
Nice to see you, by the way.
Here.
Right. A green arrow, you press it, and then you choose.
Oh,
yeah, now you did it.
and
then
I can make the full size. Yeah.
Yeah. Now you press that, and it will be the slide mode.
I got
Excellent.
it. Hello, everyone. Let me first thank the previous speaker who talked about super resolution microscopy, and this indicates the fact that singular optics, structural optics, moves down to very high resolution, to the resolution of nanometers. Because of that, there is a high need for the tools to study the structures, the structured light. And in this case, the most efficient tools in this wavelength range is the fluorescence. And for introducing fluorescence, for using it efficiently, we need fluorescent dyes. And now I am going to present you an absolutely new type of dyes, which are based on quite different methodology, which probably people involved in optics could not find it in the mass of current literature. Because the origin of this work comes from quite a different field, the field of modeling the transfer of ions in biological systems, particularly in biological membranes. The special feature of these dyes is that being excited, it generates the fluorescence beam, but it binds the ions to one terminal of this molecule, and on transfer of electronic charge on excitation, the charged ion moves to another opposite binding site with strong change of fluorescence. It is this strong shift, I will show you, the strong shift of fluorescence energy, which means this shift of wavelengths, and this fact can be observed as a function of time in this picosecond some nanosecond time range. Well, this idea comes from bioenergetics, the motion of ions to biological membranes, and we were surprised by dramatic response of these dyes in terms of color. And I think that optical photoselection, according to polarization and spin, which is needed, may be realized in these structures, and which come from just biological field. We needed to explain the coupling of energy applied to specific molecules, which could move the ions against their concentration gradients to accumulate in high concentrations, either outside this, moved outside this the cell or inside the living cell. This problem is very, very extremely important in biology, probably the most important problem, how different types of energy are interconverted in biological structures. We have we have such molecule which can transfer protons in a rather simple way, coupled with isomerization of the central pigment, but we do not know, do not understand the energetics, the kinetics of these problems. It's more difficult to say about the systems of photosynthesis, which are quite complicated. Even in a simplified scheme, we can observe that this central pigment absorbs 4 quanta of light. Why 4 quanta of light? And the reaction occurs in a quite different site. It splits water, producing protons and oxygen. But what is the connection? What is the mechanism of transformation of energy is not known and not understood. Working just between physics and biology, I observe always the lack of understanding between these fields. Physics wants to know not only molecular structures, but how they operate. What in energetics and kinetics terms. Biologists have known this means, and biologist is satisfied only by structural aspects, by knowing what comes out from different reaction passing through different steps. But energetics and kinetics of these steps, for instance, how the transformation of energy due to splitting of ATP is transformed to ion motion across the membranes. So Richard Feynman said, what I cannot create, I do not understand. I would say, what I do not understand, I cannot create. So we have to understand first and then to create. What could be the solution? Solution can be searched in quite different areas. And one of these areas is the area of molecular machines. These 3 gentlemen got the Nobel Prize when they showed that rather simple structures on supply of external energy can rotate or translate within different directions, resembling the motion of molecular machines. What is the principal mechanism? The principal mechanism is that no simple reversibility. Chemical principle of reversibility is broken, and you can only move according to the cycle. This can be realized when molecule moves along the thread, or when the molecule is rotating. Molecule is rotating only in one direction. To achieve that, you need to input the energy of one quantum on one step, and to go back on different direction, on opposite direction, to input of the other quanta. This idea has stimulated our studies, and we decided to follow quite a different way. To use the light in all the studies, previous studies of molecular machines, the light energy was used to change the energy profile to make the circular motion. Our idea was to use the excited state energy directly. This idea was realized in a number of recent publications, which again was in the chemical field. My task is to attract the new possibilities to more extended audience, including optical physics. Well, we use the dyes which specifically provide charge transfer in the excited state. And this charge transfer can be coupled to proton transfer. Why that? Because it's very convenient to move the spectrum to longer wavelengths at a large distance with sufficiently good separation to follow these reactions. So we follow the reactions of charge transfer, and we can follow the reaction of ion motion. I will tell you how this happens mechanistically. This is what happens with molecular machines. 2 strokes. We need only 1 stroke. One energy input by excitation, and then part of the cycle goes along the excited state, then the emission or non-emission decay, and the second part in the ground state process. So how our molecular works? In the ground state, molecular has a charge at one terminal. In the excited state, immediately it attains strong dipole moment due to the presence of this charge and the pi-electronic system within the molecular. Then the charge transfer appears to another site, which is created by charge transfer reaction, and the dipole moment is reversed. And then decay to the ground state and the closing the cycle. How this happens with the ion? The ion is bound first to one side, then goes to the opposite side with dramatic shift of spectra. And this is the complete scheme. The excitation, charge transfer, reversal of dipole moment, then ion translocation, and the back reaction. What we see? We see this band without ion translocation and this is the resolution between two bands. In one of the cases with smallest die, the shift. The shifts can be much larger when with the variation of the length of the structure of the die, and we observe the motion from blue-green range of spectra to red and even near-infrared range of spectra. Very strong change of color. And this color provides the information about the structure, about the fields surrounding this molecule. And this process can be followed in time domain. Look, blue-green band at initial times, and along with the ion motion, we move to the red band. So from blue to red, we have very strong change of fluorescent color due to motion of dye. And the motion can be modulated, as let me stress, by different factors, which have to be studied because these are new dyes and these are only initial studies of these types of mechanisms. Time-dependent ion motions can be followed as a function of ion size and mass, as a function of temperature, as a function of viscosity of the medium, of any other parameters which you want. We can extend enlarge this possibility by putting at the accepting site the additional site for intramolecular proton transfer. And in this case, the bands are very well separated, and including the increase of brightness. Here should be fluorescence when there is no charge transfer. Here is the band with charge transfer plus proton transfer. And here is the band when the ion moves to a new binding site. Very impressive. And this process can be modeled on a time scale, and the characteristic time is around 100 picoseconds. So the ion could be not necessarily to return to initial position. It could be transported to another new binding site, which can be organized, for instance, in biological membrane. This is an important extension of our work, and it should justify our efforts to present this dye as a molecular machine. Molecular machine should do work, so the ions should be taken from somewhere and accumulated somewhere else. And completing my talk, let me stress that the theoretical and experimental work is needed to analyze the interaction of strong and changing molecular dipoles with external fields of different structures, or structural fields, and convenient multicolor fluorescence response can carry this information in energy and also in time domain. So potential applications which can be realized, I expect that, they can be realized in the studies of nonlinear optical fields, singularity points, etc. Can be extended to sub-wavelength spatial domain up to several nanometers and to sub-nanosecond time resolution. Let me finally acknowledge the participants of this work. The work was initiated by my partner, Peter Cho, of the National Taiwan University in Taipei. The synthesis was made, some of the synthesis was made by scientists working in Finland. And Peter Cho has a team of bright students, very dedicated students, both in synthesis, in analysis, and photophysical studies in the group of Peter Cho. So thank you very much for your kind attention.
Thank you very much, Alexander, for this mind-opening presentation, I would say. Very interesting effects. So now we have 13 minutes, more than 10 minutes for discussions and questions. And I already see that Igor has a question. Please, Igor, go ahead with the question.
Thank you. As I understood correctly, your approach works for some kind of molecular, yes?
Mm-hmm.
Is that right?
Yes, definitely.
Can you say about the range of media which we may investigate with your approach?
Well, the range, I stressed the optical range. And the range in applications in different media could be probed in experiment. I cannot predict that. The only thing that I can predict that the dye has relatively high photostability for studies for attempts in studies for super resolution microscopy. But a common confocal microscopy can be easily applied.
Thank you.
Do we have more questions? Maybe I can ask, but I'm interested when you speak about ion transfer.
Mm-hmm.
Is it the real, like the whole atom moves, or just the electron jumps to the other side?
Well, the story is that here the ion is attached electrostatically. The medium is selected with low polarity. So the electrostatic attraction is strong.
I'm
then
sorry, Alexander. The blue one is an atom. Is an ion. It's not an electron.
the ion, is an ion.
See.
An
Yeah,
ion.
I see. Yes.
An ion, and positive charge is intentively located at one side of the molecule, and he is the pi electronic network. So the partial charge, electronic charge, moves along the molecule in the excited state, creating a new charge, a new binding charge for the ion.
I see, right.
Yes.
So the charge
And
moves,
then-
and then it attracts the ion. First the charge moves, and then it attracts the
and
ion.
ion moves again by electrostatic force.
Right. Well, this is quite a fast effect, right? So it's like sub-nanosecond, right?
Yes.
What is the time scale?
Maybe at very high viscosities, it will be longer. But again, the process of motion should occur within the excited state lifetime. When the emission decays, when the excited state decays, the binding site also disappears.
Yeah.
So this is the limit. We have to limit the studied phenomenon, if it is a kinetic phenomenon, to nanosecond, sub-nanosecond time range.
Yeah, I see. I know that that most of the molecular machines based on azobenzene molecules, isomerization, they are still quite slow, right?
Well, there is a trick. Isomerization is slow, maybe slow, but isomerization, the energy of isomerization, of excitation energy for photoisomerization, changes the energy profile for the motion, rotational motion or translational motion, that can be slow and occur in the ground state. So excited state is used only to create the energy profile. In our case, it is quite different philosophy. The excited state energy moves the structure. In our case, moves the ion.
Yeah, I see. And I have one. Maybe somebody else has a question. Please, anybody, you can join the discussion. Just switch on your microphone and join the discussion. Anytime. But I wonder here, in this slide, the whole process includes fluorescence. Can you replace fluorescence with a stimulated emission to accelerate the process?
Well, we did not do that. And again,
I mean, the fluorescence is a slow process, right? But if you replace it with a stimulated emission, then you can accelerate the cycle.
Well, first we will have the narrow bands, and should we accelerate? I'm not sure that we will accelerate the ion motion.
Yeah, what is the fluorescence lifetime? It should be several nanoseconds, maybe.
Yes, around nanosecond.
Yeah, right, some nanoseconds, but the processes of the ion transfer maybe hundreds of picoseconds.
Yes, exactly.
So with the stimulated emission, you can make the fluorescence instantaneous.
Well, we can make the emission shorter and more narrow. But now I have to think, but now I don't see the advantage.
Yeah, I see, right. So it's fast enough in your opinion, right? So please, anybody, ask some questions. We still have time. We have 5 minutes.
Yes, I intentionally made my presentation so short.
Mm. And the spectral change is huge.
Mm-hmm.
This is a very, very interesting. So it is so
Right.
obvious, this huge like spectral shift. And the shift is not anyhow connected to any Stark effect, right? It's a Stark effect. It's because we have a new molecule.
Yes.
The new compound, I would say.
Stark effect may appear when external field is applied, maybe. But
yeah, I thought that if you move
the effect is just electrostatic effect.
Yeah, I see. I thought that if you move the ion together with its electric field,
Mm-hmm.
then the local Stark effect can change the spectrum.
Yes.
Yeah.
It's the effect which in fact moves changes the energy and moves the spectrum to the long wavelengths.
Mm-hmm.
Right. This is the mechanism why the color changes.
Yeah. Right.
I have a quick question. Hello, thank you for the great talk. This is not my specialty, so I just have two questions. One is linked to the previous talk. How do you think this molecules can be used for single molecule fluorescent microscopy for imaging? And second, I maybe missed it, but is there a reference where we can read more about this?
We have to try. In fact, single molecular studies are reasonable and are applied with the system in which you have to resolve the complicated structure, such as living cells. We are not on the step to apply these dyes in this way. We need primarily sorry.
Alarm in Ukraine, yes.
Alarm, we have Sirena.
But we continue our presentations, our session. I'm sorry. Continue, please.
So for doing that, we need to design a more complicated structure. Probably to supply this dye with additional functional units.
What about the reference? Some published paper with the results. Do we have any published paper with these results?
Huh? Oh.
Do you have any published paper where we can read more?
I showed you some papers which we published already.
Okay, good.
Yes, and I stress that these are top journals, but the journals of general chemistry. Physicists do not read these journals.
Yeah, when you Google, specific terms,
Yeah.
then
Okay.
you can find.
Okay,
But,
I took note of them. Thank you.
all right, thank
I'm
you
sorry,
again, Alexander.
Russian attacks, but we continue our session. Russian attacks.
Yeah, all right. So thank you again, Alexander, for the presentation. And so our next speaker is Aymeric LERAY from France. And the talk is about computer-assisted multimodal microscopy for quantified molecular diffusion in cells. So
yes.
you
Hello.
can hello.
So I will share. Can you see my screen?
Yes.
Yes. Is it okay?
Yes.
Okay.
Everything is fine.
Okay, thank you. Thank you a lot for giving me the opportunity to present this work. So, as you already say, I will speak about multimodal microscopy assisted with AI for characterizing molecular diffusion. So, let me first introduce temporal dynamics of some biological process. So, you can see here that the domain's movement is around microsecond, and that the protein folding is around a millisecond. The time required for a protein to explore the cell is around 1 second, and the protein synthesis is around a minute here. So to measure these dynamics, there exist several optical techniques depending on the temporal resolution and the number of molecules. So the pump probe techniques here is can measure ultra-fast dynamics, but it's limited to my mouse. But it's limited to it's not easy to use in cell. So as you can see here, when we are interested in molecular diffusion, we would like to measure dynamics around milliseconds or between microseconds and minutes. So indeed, for this kind of scales, we will use mostly fluorescence correlation spectroscopy, FCS, or SPT, single particle tracking. So this is the two techniques that I will present today. So first, principle of fluorescence correlation spectroscopy is very simple. You just need the laser to focus into your sample, and then you will look on the diffusion of the molecules that will go through this volume. So you will record the temporal fluctuation of your intensity. Here, this is the intensity signal. Then you can calculate the autocorrelation by multiplying your temporal profile R with the shifted fluorescence profile, and you normalize with a mean of your intensity. And what you obtain is, for a small time shift between the two profiles, you have a large correlation, so you have the maximum of correlation. When you increase here your time shift, you lose your correlation, so you go through zero. And then you will add a model in order to fit this correlation curve, and you can retrieve the number of molecules here, which close to the G0, and you can have also information about the diffusion time of your molecule inside your focal volume. So now I will investigate more precisely the transcription. So this work is done in collaboration with Laurent Elio in Lille. So we know that all cells have the same genome, but they don't express the same gene over time. So it's well known that the RNA polymerase is implied in the transcription, but how it finds the right gene is still an open question. So to answer this question, we have investigated the dynamics of polymerase. Because the cellular environment is very crowded and heterogeneous, we cannot use a standard Brownian motion, but we will use another diffusion model, which is the anomalous model. So in this model, there is it will depend on the coefficient diffusion and also on the anomalous exponent here, the alpha parameter. And if this parameter alpha is equal to 1, we retrieve the standard Brownian motion. But if it's larger than 1, we have a super diffusive model. And if it's lower than 1, it's a subdiffusive diffusion. And so we have applied this model to dynamic of polymerase in a cell. And we obtain here, this is the result that we obtain. So in fact, we find that the anomalous exposant is lower than 1. So it means it's subdiffusive. We find 0.6. And the residence time is around 60 milliseconds per micrometer square cube. So if CS gives us the first parameters, then we have also applied SPT, so single particle tracking. So for the principle of single particle tracking is to acquire a stack of images, and then these images contain some spots corresponding to, in fact, one fluorescent molecule. And then when we record a movie, we can then after retrieve precisely the center of each fluorescent molecule by fitting with a Gaussian. And then we do it for each image. And in fact, we obtain a trajectory here by linking the different spots during time. So we can obtain a trajectory of movement of a fluorescent molecule in cell. So then I will show you here an example of one trajectory recorded of again for the polymerase. So you can see the trajectory, it's not so long, but we can see a small trajectory here. Then after, to retrieve the diffusion, we will use the mean square displacement here, which is just the difference between the two coordinates that we normalize. And again, we can use the diffusion model. So if we fit this mean square displacement as a function of time, it can give us some information, because if it's linear, it says that it's a standard Brownian motion. If it's subdiffusion, we obtain again the alpha exponent smaller than 1. And if it's super diffusion, we find an alpha exponent that is larger than 1. So we have applied this model to our data, and indeed, of course, all trajectories are very noisy, but there is a large variability between the different measurements. But we could find two populations. One population here in one which has an alpha exponent which is close to 1, in fact. And the second population with an alpha exponent lower. And you can show here the distribution of the population. And I show you here the values. So indeed, we find one population with an alpha exponent close to 1 on a residence time of 4 milliseconds, and then a second population with an alpha exponent lower than 1 with a residence time longer. So just to summary, we have used two different techniques. So with FCS, we find a fast anomalous diffusion with an alpha exponent of 0.6. But the problem is that FCS cannot detect immobile molecules. It can just see some mobile molecules. So maybe we can miss one population. And with a single particle tracking, we obtain two populations, one with a Brownian motion and one with a slow anomalous diffusion. But the problem with the single particle tracking is that fast diffusion cannot be detected because we are limited by the acquisition time of our camera, and the exposure time is around 10 milliseconds, so we cannot detect dynamics faster than 10 milliseconds. So the question is, how can we interpret these different data? So Based on this incomplete data, we propose two different mechanisms for explaining the recruiting of polymerase. In the first one, there is different successive steps. First, the polymerase diffuse freely, then it can enter into a large confined domain, and then after enter in the second subdomain with higher confinement. So this is in agreement with theory of TAT topological associated domain here. But the second model could be also that there is different confined domain. So first, again, the polymerase could diffuse freely, then it can enter into two different domains, one fast oversampling or a second one with slow oversampling. So in this model, it means that there is different mechanism for recruitment of polymerase. So in fact, I already showed the conclusion. So it's not possible to conclude with this data. So we need simultaneous SPT FCS measurement because for the moment, two different techniques are used in two different setups. So we cannot compare directly the same data. So this is the objective of this project. So for that, we have two possible options. The first one is to use a single point system. So in this one, main difficulty is that the focal volume of the two techniques, FCS and SPT, should be the same, so it's not easy. But we have still started to try to do this kind of setup. Second possibility, so with this setup, we could start to reply some questions because we can start first to point with FCS into close to transcription factor, to close to the zone where we have activated the transcription, and then we look on the diffusion of the molecule in close to this volume, and then we can check with SPT if we obtain also the second population. But this model will be limited because we cannot check the complete cell. We will just have access to one point in the cell. So the other option will be to use a multi-point FCS system. So in this one, we will use a single photon avalanche photodiode array. So on this array, we will have access directly at the same time to the temporal dynamics and to the position in our image. So we will have the spatial and temporal dynamics for data. Okay, so the thing is that with this system, we will have some multimodal data which are complex because they are obtained with two different systems. This spatial temporal data will be heterogeneous, and of course, there is a multi-scale dynamic. So the analysis of these data will be difficult. So we have started to implement some method based on artificial intelligence in order to analyze this complex data. So if we want to use AI, as you know, we will need a lot of data. So for the moment, we don't have enough experimental data. So we will started with simulation. And the difficulty is that for simulated anomalous diffusion, there is this different physical model. So the first one, so I show you three models here, but there is more models that can explain anomalous diffusion. But let's start with these three models. So we have used the fractional Brownian motion. In this model, you consider that there is a correlation between two consecutive steps, so there is a memory effect. We have also considering the continuous time random walk. And in this model, there is two different distribution, one for the weighted time and one for the jump length. But this model is non-ergodic. But on the last one that we consider now is a random walk on a fractal. So this time the walker will move on a fractal geometry object. So we have used these three models, and we have also, of course, considered the normal Brownian motion model. So this is the 4 diffusion models that we have considered. We have varied the alpha exponent and we have varied the diffusion coefficient. And we have also varied trajectories, so length of trajectories, and also varying the focal volume of our microscope. So in total, we have generated more than 3 million autocorrelation curves. So this work was done by Aymeric team. It was just for FCS analysis first. And in this work, so performed by Aymeric team, they use a histogram gradient boosting classifier. So their methodology was made in 3 steps. The first step was they use histogram gradient boosting to classify and finding the good model. Then they use again histogram gradient boosting classifier for quantifying, so for retrieving the alpha exponent and the diffusion coefficient. And they use a third time a classifier to consolidate the data. And I show you only results that they obtain on some experimental data, which are beads diffusing into glycerol. So you can see, in fact, that they retrieve for each, so they change the concentration of glycerol. So when you change the concentration of glycerol, it should change the diffusion coefficient of your sample. So they retrieve that the model is mostly Brownian motion, which was expected. And so here they retrieve also the alpha exponent, which is close to 1, we would say. So in the molecule, machine learning was in blue, and in orange, this is the result of the fitting method. On the last part here, this is the estimation of the diffusion coefficient. So you see that when you increase the concentration of glycerol, you decrease the diffusion coefficient of your sample. So it was promising. So it kind of worked for FCS data. So the advantages of machine learning is that you can identify the diffusion model, which is not possible with fitting, because when you do fitting, you need first to choose one model. So you see also that does not require any analytical expression for the model, and also they show that it works for short measurements, so 250 milliseconds. So it was for SPT. The second part of our work is about, no, it was for SCS, sorry. So now the second part of the work is for SPT. So again, there was some work that was done for analyzing SPT with AI, and it was done in 2021. It was called the Anomalous Diffusion Challenge, so ND challenge. So in this challenge, there was 3 tasks. The first task was to try to retrieve the anomalous exponent. The second task was to classify the different diffusion models, and they consider in this challenge, they consider 5 different models. And the third task was to segment the trajectory, but I will not speak about this one today. And I show you here the best method that was for the classification task. And you can see that the best methods called here, so for 2D and 3D, for the two, they are based on neural networks, NN here, or they are based on recurrent neural networks, or LSTM means long short-term memories. So all these algorithms are quite well known now, so it could be interesting to see if we could again improve this result by using more recent algorithm based, for instance, on transformer or selective state space model. So for transformer, if you are not used with that, the transformers, they are in fact used for natural language processing. So they are based from ChatGPT that maybe you use. And you could also use this kind of algorithm in vision or time series. So this is the objective of this work. The interest is that it can capture long-range relationship between the different trajectory points. And of course, it can handle a large data set with parallel processing. So I will not have time to detail each part of this algorithm, but you have here an encoder and here the decoder part. So it's an encoder-decoder structure, and it's kind effective, very efficient for analysis data. The second model that we have used is again more recent because it was developed in 2023, this one, and it's called Mamba, so it's a selective state space model. And this model, in fact, was developed to address some limitation of transformer, especially for long sequences. And in this model, it focuses only on relevant information. So interest is that it can discard very easily the irrelevant data. And again, because you can see the architecture is very simple, so because it's simplified compared to transformer, it can also be parallel, so it will be faster than the transformer. So now, again, we will need to do some simulation. So for this part, we have used 5 different models. You can retrieve the fractional Brownian motion that I presented before. On the continuous time random walk, we have also considered annealed transit time model with trapping time, the LERAY walk, which is a super diffusion model, and scale Brownian motion. So for now, we have only considered diffusion in 1D, and we have considered a fixed trajectory length and a fixed alpha exponent. And it's the reason why the number of trajectories is quite not so much high. We just use 200,000 trajectories for this work. And this is the first result that we obtained. So you can show here if we do not, so if we consider that the trajectories there is no noise in the trajectories, so they are perfect simulated with the diffusion model, we obtain that the long short-term memories is the first one, and the second one is a selective state space model. And then after we have started to add a little bit of noise to the simulated data. And as soon as we had like 2% of noise in the trajectories, we find now that the best model is a selective state model. And in fact, after is a convolutive neural network. And if we increase the noise, still the selective state model is still efficient. And so in average, we can see that this is the best model for the moment. And another thing which is important to compare is the training time. If we compare the training time necessary to each model, we see that this selective state space model is quite fast compared to long short-term memories, for instance. So this work is done with Renato Martins and Cédric de Monceau also in Dijon, in France. And so now sorry, I'm too long. I will just, the final objective of this work is to be able to analyze in real time the diffusion of polymerize in the nucleus. So for that, we will need to learn simultaneously multimodal data based on FCS and SPT in order to classify and quantify the diffusion of the polymerase. So I would like to thank Laurent Elliot team in Lille in France also. I would like to thank my colleague in Dijon in France and my colleague in Mulhouse, Alain Dieterlin, and his team, and Torsten Holland in Singapore. And thank you for your attention, and sorry for a little bit too long.
Thank you very much. An interesting topic. Do we have any questions? So I have a question. It's like in general, independently of the technique you use, for how long time you have to watch the molecule move in there in order to be able to characterize the diffusion process?
That's an interesting question. So in FCS, you need around 30 seconds to just 30 seconds. So you record the fluorescence intensity during 30 seconds, and then normally you should calculate the correlation of your signal. With SPT, because it's a single molecule system, so you need to do it a lot of times. So for one molecule, you can follow it, let's say 30 seconds. But after you have a different problems. So one problem could be the photo bleaching. But the major problem is that the molecule will go out of your focal plane. So you will lose the molecule. So in fact, you can follow the molecule a very short time. So like 10 points. So 10 points for your trajectories is okay. So it means that you need to repeat this process a lot of time in order to have enough trajectories to characterize your data.
Right, or maybe you have to watch many molecules simultaneously, and then the time can be shorter, but then you need the most sophisticated.
Yeah, you cannot watch them simultaneously because you want that they are individual. So you need to. So there is So it depends on the technique that you use, but maybe sometimes you can use a first flash to just activate few molecules in your cell, and then you follow this few molecule until you lose them, and then you start again with another flash, and you follow other molecules, and you start again.
All right, thank you very much. All right, now it's time to move to the final presentation in this session, and it will be given by Alexander Ushenko. I suppose I pronounced it correctly, the name. And the presentation is about 3D digital polarimetry of diffuse biological tissues objects.
Okay, thank you very much. Just a moment. Do you see?
Yeah.
We see.
Yes, okay. Good afternoon, dear friends, dear colleagues. My name is Alexander Ushenko. I am a professor of Yuri Fedkovich Chernivtsi National University and high-level expert of Taizhou Institute of Zhejiang University, China People's Republic. The title of my report, 3D Digital Polarimetry of Diffuse Biological Objects. Short outline, introduction, Mueller matrix differential of the depolarizing biological layers, optical scheme and methods of layer-by-layer 3D Mueller matrix mapping, layer-by-layer maps of phase and amplitude anisotropy parameters of partially depolarizing polycrystalline blood films, differentiation of polycrystalline blood films from healthy donors and patients with prostate cancer. Oh, sorry, just a moment. Where is my ekran? Okay. Just a moment. I start again. Do you see?
We see, right. We see the introduction.
Oh,
right.
okay. At present, methods and means of Mueller matrix polarimetry of the structure of biological tissues are being actively developed in biomedical optics It includes a number of original directions. First, research of scattering matrix, Mueller matrix polarimetry, polar decomposition of Mueller matrix, and two-dimensional Mueller matrix mapping. Traditionally, the methods and tools of the Mueller matrix polarimetry have been developed within the framework of two limiting approximations. The first is the search for relationships between angular and coordinate distributions, the value of the Mueller matrix elements, and the structure of optically thick depolarizing biological tissues. The second is the Mueller matrix polarimetry of optically thin, non-depolarizing biological layers with subsequent reconstruction of the distribution of the parameters of phase, birefringence, and amplitude, dichroism, anisotropy. At the same time, most biological objects are partially depolarized. Therefore, the further development and generalization of Mueller matrix polarimetry techniques of the 3D polycrystalline structure of biological layers with different light scattering multiplicity or different depolarizing ability is urgent. Such a possibility can be provided by a combination of methods of differential Mueller matrix and holographic mapping of phase in homogeneous layers. Our work is the development of depolarizing studies by experimental testing of the 3D Mueller matrix mapping methods with digital holographic reconstruction of layer-by-layer distribution of the optical anisotropy parameters of partially depolarizing biological films and the determination of objective criteria for the differentiation of polycrystalline blood films from healthy donors and patients with prostate cancer. Next stage of my report is information about short theory of our methods. You can see equation 1, the interrelation between the changing of the structure of Mueller matrix operator in the plane Z and Mueller matrix W, Mueller matrix, Mueller differential matrix. This matrix operator consists of parameters which conclude the values of the linear dichroism and linear birefringence for the different directions of the optical axis, such as 0 degree and 45 degree. And the last type of optical anisotropy is circular birefringence and circular dichroism. In general, this matrix operator can be write as a superposition of two parts. The first part, you can see the equation 3. The first part characterizes the fully polarized properties of the biological layer and consists of the average value of the parameters of the optical anisotropy. The second part describes the fluctuation of these parameters and name the depolarization part. We obtain the interrelation between the average value of the optical anisotropy parameters, phase anisotropy, birefringence, and amplitude anisotropy, dichroism, and values of experimentally measured Mueller matrix element RGK. In the next equation, 5, 6, 7, 8, 9 describes the main algorithm, how we can reconstruct the value, the average value of the linear birefringence, circular birefringence, linear dichroism, and circular dichroism using the information about experimentally measured Mueller matrix elements. In experimental patch, of our method, we use the polarization in Mach-Zander interferometer. You can see this optical scheme. This is helium laser spatial frequency filter The next block is the polarizing filter, which construct different type of polarization of the incident beam. Beam splitter 1 formed two channel. Reference channel is this interferometer and objective channel. In reference channel, we use the intensity regulator, which consists of two linear polarizing. And in objective channel and the reference channel, we use two types of polarizing filters, which formed 6 types of polarizing of the laser beams, such as 4 types of the linear polarizing with the azimuth 0 degree, 19 degree, 45 degree, and 135 degree, and 2 types of the circular polarization left and right. By using beam splitter 2, we formed the interference pattern in the plane of the biological sample. We use the optical layers of the blood. And this interferometric patterns, you can see this as example, by the polarizing micro objective projected to the pixels plane of the CCD camera through the linear polarizer and analyzer. Using this technique, we can obtain the equations for the analytical reconstruction of the distributions of the complex amplitude of the objective film of this sample. The main algorithm is, you can see the equation 9. This is a 2D digital Fourier transform. This one, the coordinate distribution of the intensity of the interference pattern filtered by analyzer. You can see again this analyzer, and we rotate the plane of transmission of this analyzer in two situations with orientation 0 degree and 19 degree. Reconstructed complex orthogonal or reconstructed distribution of orthogonal component of the complex amplitude of the objective film of our blood layers. You describe these equations, and using this equation we can calculate the values of the several Stokes vector parameters. You can see the equations 11 for the 6 type of the polarization of object and reference beams in the polarization interferometer Mach-Zander. Next, you can see the interrelation between the values of the partial elements of the Müller matrix of our biological layer and the superposition of the values of the Stokes vector parameters 1, 2, 3, 4 for the different type of the polarization in our scheme. Using this interrelation 12, we can obtain the algorithm for the reconstruction, the value of the average value of the linear birefringence for direction 0 degree, linear birefringence for direction 45 degrees, circular birefringence, and another parameters of amplitude anisotropy, linear dichroism, and circular dichroism. The first part of our experimental investigation was the reconstruction layer by layer maps of the optical anisotropy, the layer of blood which was taken from a healthy donor. On the left side, you can see the maps of the phase anisotropy, linear birefringence and circular birefringence. On the right part of our slide, you can see the analogous maps of the amplitude anisotropy, linear dichroism, and circular dichroism. These maps was obtained in different phase plan of the reconstructed objective film of the blood films. You can see the coordinate structure of these maps very coordinate inhomogeneous. And for the objective analysis of these maps, we use the calculation of statistical parameters as statistical moments of first, second, third, and fourth order. In these dependencies, you can see the dependencies, the value of the statistical moments of the first order for the linear birefringence, circular birefringence, statistical moments second order, statistical moment third order, and statistical moments of fourth order. You can see the a big interval of the changes of its own value. Analogous dependencies we obtain for the statistical moment for the parameters of the amplitude anisotropy. This information we used for the found of the markers for the differential diagnostics of the blood film layers from healthy donors and sick patients with prostate cancer. On the left side, you can see the maps of the optical anisotropy, linear birefringence and circular birefringence, healthy donors, left column, and patient with prostate cancer, right column. Analogous, on the right side, you can see the maps of the linear and circular dichroism, healthy donor, and patients with prostate cancer. In this table, you can see the intergroup differences of statistical parameters characterizing maps of linear and circular birefringence and dichroism in optimal phase sections. These sections where the difference between the statistical moments is more bigger. If you see on this data, we can see that the most sensitive parameters to the pathological changes of the blood films are the difference between the kurtosis, which characterize the optical anisotropy maps of circular birefringence and circular dichroism. This you can see the value of the accuracy of the difference diagnostic of the prostate cancer. You can see that the value of the accuracy more than 19%, 19.3 and 19.5.8%. And the last table give information about comparison of the different effectiveness of differentiation diagnostic using the traditional methods of polarization mapping. We can see that the accuracy very low. The traditional Muller matrix mapping, the accuracy more high, but the level is not satisfaction. And our methods layer by layer mapping, we obtain the high level accuracy equal 19.3 and 19.4%. Finally, The proposed and substantial method for 3D Müller matrix reconstruction of the distribution of the parameters of linear and circular birefringence and dichroism of partially depolarizing polycrystalline blood films. The dynamics of changes in the magnitude of the statistical moments of the first fourth orders characterizing the distribution of optical anisotropy parameters of the polycrystalline blood film of the healthy donor in different phase sections of their volume has been investigated and analyzed. The most sensitive to prostata cancer parameters were revealed as statistical moments of the third and fourth orders. The difference between this value is maximum. An excellent accuracy, more than 19%, 19.3 and 19.6%, of differentiation of samples of polycrystalline blood films from the different group of patients was achieved by the method of 3D Müller matrix reconstruction of the distribution of phase and amplitude anisotropy. And comparative studies show the higher effectiveness of our methods layer by layer phase scanning of the object film blood layers. Thank you very much for your attention.
Thank you very much. This is indeed a very important investigation. Now we have enough time for several questions. Please ask questions. Right, maybe I can start. The circular dichroism and birefringence differ for the healthy patient and a sick patient. And what makes it differ? Does the blood contain some chiral molecules and the concentration of them is different?
Yes. When our object was the dehydrated blood drop on the glass. During these processes, the molecules which consist the blood plasma and formed element create the supramolecular networks. And the structure of these supramolecular networks is optical anisotropy. The long molecules, albumin molecules, construct the networks like dendrite networks and formed the structural anisotropy like linear dichroism and linear birefringence. And the optical active molecules, like globulin molecules, is the optical active and forms the circular birefringence and circular dichroism. When we investigate the blood from the health donors and the sick patients, the structure of these supramolecular networks are different because the concentration of these molecules in the liquid blood similar. And if we use the biochemical methods, we can not to make differentiation between these peoples. Using the structural analysis by polarization methods, we can differentiate because the structure of the supramolecular network forms a different type of linear birefringence and linear dichroism. And we used these parameters for the differentiation of this state of the human organism.
All right, thank you for the explanation. Now we have a question from Igor. Igor, please go ahead.
Yeah, thank you. Maybe I missed something, but it seems me you did not say about the stage of cancer. Can you say about this?
Yes, I understand you fully. Thank you very much, Professor Mohun. This I give information about the differentiation healthy people and people who has prostata cancer. But this process, pathological process of prostata cancer, has four stages, and there are the international describe of this stage. We investigate in this. And have information we can differentiate in different stage of the prostata cancer. But in this report, I cannot give this information. But if you want to give this information was published in 3 journals: Frontiers in Physics, Journal of Optical JOHS, Optical Health Technologies, and Journal of Biomedical Optics. In these articles has detailed information about this.
Thank you.
But do you think that the technique can be applied to diagnose the cancer in its early stages?
Yes, the main and significant task, you are right, fully. The main and significant task, the detection of early stage and or the first stage of the prostata cancer. We obtain the results with higher accuracy, and we can do this on the stage where the biochemical methods don't see this.
I see.
But the main problem, biomedical problem of the practical interpretation of this, we must investigate a great number of people. We cannot do this. We can involve in this investigation many clinical and treatment organizations. They are very difficult, but we give the methods and we propose how do this, and we hope that this is methods found your practical application. But for this needs a very big volume of money.
Sure. But if it enters the market, then you can also get the money.
Yes, but not for us. For our government, for government in other countries.
I see. Right. Any other question from the audience? No. Okay. If there are no further questions, then I think we can close the session. I want to thank again everybody, every presenter, because I think that the session was very successful. Very important results were shared between other scientists, and this is the most important stuff that we do on the conferences. So I thank very much every of the presenters today.
Thank you very much, Professor Shevchenko, for your nice management of this part of the conference. We are greeting to you and thanks for this. Thus, we have a short break for lunch. We start another part of our session, the second session, at 1:30 p.m. With another Zoom link, and the closing ceremony will be today as well with another Zoom link as well. Thus, we meet you at all of us at 1:30 p.m. Thank you.
Thank you.